It's not a, I think it's a fairly strong condition on that set of functions because of these theorems we have about Wronskians and so forth. That's an itch I have not entirely scratched yet in this course. But I think if I ever do, students will never take my course again. So, all right, that brings us to reduction of order. Reduction of order is an important technique, which I've already skipped over in the first order case. Perhaps we should look at it in a little bit. Basically, the idea is that you can, well, reduce order. And it has, sorry, it's kind of stupid. These identities are crucial to that. And, you know, these identities don't get enough airtime in Calc 1. They ought to get more airtime. There is this some kind of like, you know, second product rule or kth product rule. Here it is. Oh, that's supposed to be an n. How did I get a b there? Good job. Why? Anyway, so the nth derivative of a product, you take binomial coefficients, right? So it's like the binomial theorem essentially, but with derivatives, you know. And there's always n total derivatives there, but you have n minus k on the f, and you've got k left on g. So in total, you've got n derivatives on each term, right? And that's the general, you know, the n-fold product rule. And if you use that, let's see here, you make a substitution like y2 is equal to v times y1, where y2 is a solution to the homogeneous problem, then what does that tell you? If you plug that in, it ends up reducing the order, I believe. I'm trying to remember. I don't teach this as much, but it's kind of a lost technique in my opinion, which is unfortunate. It's really neat. Let's see here. Get to the point. Oh, come on. Where was my point? I think this talk is pointless at this point. I'm sorry. Oh, yes. Well, what we usually show, actually, I mean, okay, so I remember. So the thing I usually derive for students in a class is this result for n equals to 2. But what I was just showing you is kind of the corresponding nth order reduction of order. But maybe I should just do the n equals 2 since I won't butcher that as much. I mean, what I'm trying to say is that what I was just not explaining or starting to explain is what's past this example. Now, this example we always show people. What this gives us, the tool that this gives us is if you have a second order ODE, all right, and you have one solution to it, all right, this gives you a formula to find a second linearly independent solution. So it's kind of nice. It's kind of like a bootstrapping thing. It says if you find one solution, basically you can make a substitution based on that being a solution, and then you can malign the, you can massage, you can contort the original differential equation from being second order to being first order. And then once you do that, you're back in the world of first order, so you can use a standard technique to solve it. That's what's the argument here. Let me show you though. Let me just go through it. So again, we have ay prime prime plus by prime plus cy equal to 0. We have y1 is one solution of it, all right? So you guessed that y2 could be written as v times y1. Hopefully that's the guess. And so you're looking for a formula for v. If you can find a formula for v, then you found the y2. We want y2 to be linearly independent from y1, right? So I guess that means that v is not a constant. So we plug in y2, we differentiate the product, right? And that's where this Leibniz product rule comes up. You just see the n equals 2 case of it. What I'm trying to say is to do this corresponding argument for the nth order case, you need the nth order Leibniz. So you can kind of think about how this would change if we were doing this at nth order as we're going. But let me stick to n equals 2. Okay, so there's the y2 prime prime, the first, this guy, right? And then there's the, Baylor, you see in this? Okay, so you see me up there? What? All the way to the top, really. Okay, so I'm just plugging in the, v2 is vy1 differentiated twice, differentiated once, plug it in. But some of those terms go away because we know that y1 is a solution, right? So the y1 prime prime times a, and the b times y1 prime, and the c times y1 all gets multiplied by a v, right? So that drops out, and it just leaves you with these guys, right? And then you make a substitution. You let z equal to v prime, thus z prime is v prime prime. And once you've done that, what you've got is ay1 z prime plus 2ay1 prime z plus by1 z. But y1 was given. So likewise, its derivative is given. So at this point, we have a linear ODE in z and x in given functions, which I can repackage in standard form, and then I just do integrating factor method on that thing, right? The integrating factor is this monstrosity. And so, by the standard technique, we get z is c times the exponential of all that good stuff. But then, remember, that's not what we're after. We're not after z, we're after v. So then I have to integrate that, all right? So I have the integral of this integral. And then times y1, right? That's ultimately the solution. We don't care about constants, so we can make that go away. We don't need a constant, right? We're looking for a fundamental solution set, so we can always multiply by a constant, non-zero constant, get rid of it. So we can reduce that clutter and get rid of it. And there you go. And of course this, let's see here. What else? How does he get this? So this, it's a substitution. So this is what? This is a y1 substitution, right? This is like minus 2 dy1 over y1. So that's a minus 2 natural log of y1, which is just 1 over y1 squared. So basically, this integral, this piece, integrates to that. But you've got, there's an exponential here, so you have a sum of this integral plus that integral. But because you have an exponential here, it becomes a product. So you end up with exponential natural log of that, which just pops out this 1 over y1 squared term. And then the exponential of that. And there you go. That's the second linearly independent. Belu, can we see it at the bottom? Okay. That's the second linearly independent solution formula. I have asked students to derive this on tests before. It's not unreasonable. It's something I'd like people to understand. I think it's important. And Skimboardis covers it too, for example, usually. So so one of the things I would remind you guys, last time we met, one of the things I did was to find the solution set to d minus lambda to the m. And you'll notice if you study what I said there carefully, I did not explain where the x came from for the repeated solution. I just said d minus m, d minus lambda raised to the m power times y has the solution set e to the lambda x, x e to lambda x, and so forth, without so much as an explanation as to where that x came from. This lovely boxed formula gives us one explanation for that. So in particular, let's pick on a specific example. If you look at y prime prime minus 2y prime plus y equal to 0, well, this is lambda equals to lambda squared minus 2 lambda plus 1. So it's the lambda minus 1 squared. It's the eigenvalue 1 repeated, okay? So we know that e to the x is one solution. If we feed e to the x into the boxed equation, look what happens. So I have e to the x times 1 over the integral of e to the 2x. The b here is minus 2, the a is 1, right? So I get this. So that integrates to e to the 2x. That e to the 2x cancels this e to the 2x, and you're just left with the integral of dx, voila, x e to the x. So the second linearly independent formula explains to you where the x comes from in the repeated root solution. Well, it's one answer to that question. I know about 6 or 7 answers to that question. To me, it's a central question, a curiosity in this course. Where does the x come from? We'll return to that issue later. All right, so now operator factorizations you've already had a taste of, right, in the constant coefficient case. But even when L1 through Ln, if you can write your differential equation as a product of operators, L1 through Ln, where they're not necessarily constant coefficient operators, you can still solve it through repeated substitution, it turns out. So, like, what you do is you solve L1 Z1 equal to F, where Z1 is L2 through Ln acting on Y. So you pull off the leftmost operator, solve that thing, right? That's one integration, you get a solution. That gives you Z1 is this lovely bit. And then you let Z2 be the rest. And then you solve that. It's again a linear ODE. I mean, if you have the L, if I have the L's are linear, I do want them to be like nice enough. The L factors. I'm assuming that the LJ is AJD plus BJ, where now AJ can be functions, but it does have to, they do have to factor into a product of linear operators for this argument I'm doing right now to work. And then you integrate again. And so this gives you a way to integrate. If you have your nth order ODE written as a product of n operators, you can do successive substitutions and integrations. Basically, the integrating factor technique again and again and again and again on substitutions of substitutions of substitutions, and you'll end up with a solution that is built on basically these n-fold integrations. It's kind of nice. Here's an example. Solve L1, L2, y equals to 3, where L1 is x dx, and L2 is 1 plus d dx, all right? So I let z equal to L2y. So I want L1 z equal to 3. L1 was what, x? So I have x dz dx equals to 3. Separate, integrate. There gives me z, 3 natural log epsilon x plus c1. Hence, I then need to solve y plus dy dx equals to that. And I can do that by integrating factor, and I get this. And so then, in total, then I get C2 e to the minus x plus C1 plus this guy. So if you have your differential equation written as a product of, if it's factored, then you can solve through successive substitution. Now the factoring is not unique. Of course, I mean, these don't commute. These operators do not commute. So, I mean, we might wonder what you could say here, what you could say nicely. So I did before the same operators, L1 and L2, but written opposite way. So L2, L1, and when I do it that way, I end up with solution C. You see it right there. That's quite a different solution set, right? As you can see, different solution set, different differential equation, right? How do you judge whether two differential equations are the same? Just like how do you judge two equations being the same? They're the same if they have the same solution set, right? That seems too generous to me. I'd like some kind of, well, it depends on what you want to mean by same, right? Same form or same solution set? Like form and solution set aren't the same, right? I mean, it's true that x equals to 0 and x squared equals to 0 have the same solution set, right? But are they the same equation? I feel like they're not. But how do you capture that? You can't capture the difference between x squared and x with just the solution set. You need some other technique to capture that. What technique? Oh, I don't know. I'm raising a question. You can think about it. Now here is one standard problem that we can solve. We can just solve this. This is a tour de force. This is much like we were doing last time. Here there is a standard technique. So I'm gonna put this away since I can actually do it. Now the things I was just showing you, operator factorizations and the higher higher order variation of parameters. So those are things I want you to know about, but as I test this course, I usually focus more on n equals 2 variation of parameters, and operator factorization, something I might ask a question about, but it's not usually a technique I expect you to use. It's kind of on the edge of things. I don't have a lot of homework on it. You can find a lot of books written nowadays that have almost nothing to say about it, unfortunately. What I have learned about it, what I know about it, is a lot of it's from this great book by Rabenstein, I don't know. So what we're going to do here is we're going to solve the Cauchy Euler problem, then we're going to take a break. Sound good? All right. So let's see here. How can we look at this? I guess first of all the question is, what is the Cauchy Euler problem, right? So this is also called the equidimensional problem, because basically every term has the same dimension, if you want to think of it that way. I mean, so a derivative maybe has dimension -1. The independent variable has dimension 1. So a term like x times dy dx would have dimension 0, if you like, or it would have the dimensions of y, is the terminology. That's why it's called equidimensional. So here. So in this case, we look at L of y, and we'll just look at the homogeneous case. And that suffices, because we already know what to do if it's non-homogeneous. Well, we don't know yet, but we will once we know how to find the homogeneous solution, the fundamental solution set, then variation of parameters takes over. We can solve it. I mean, that's it. So it suffices then to figure out what's the homogeneous solution. All right. So, but this is the problem: x to the n, d to the n, plus a1 x to the n minus 1, d to the n minus 1. So I'm just assuming it's monic, assuming the leading coefficient is 1. For the sake of not too much talking, believe it or not, a to n minus 1 x d plus a0. All right. So this is the Cauchy Euler problem, the nth order Cauchy Euler problem. So for example, for n equals 2, what's this look like? Forget n equals 2. Let's do n equals 1. N equals 1, what's this look like? It looks like something like x times d dx, dy dx, right? Plus some constant. I guess that constant I would call a1. Y equal to 0, right? N equals 2, it looks like this. It would be x squared y prime prime plus a1 xy prime plus a0 y equals to 0. All right? Now, we didn't take this approach when we studied the constant coefficient case, right? But one of the ways you could derive the characteristic equation would be just to plug in e to the lambda x into the differential equation and let the derivative do its work. You'd end up with p of lambda times e to the lambda x equal to 0. Consequently, p of lambda would be 0. That would be the characteristic equation. There's something similar you can do here. What would a solution to an equation like this be? Like, what function could you plug in here and have hope that it would somehow work out to 0? Think about like a monomial in x, like x squared. For example, if I put x squared here, what do I get here? I get dy dx is 2x, right? So I get a 2x squared plus some number of x squared. Or if I put x cubed, I got x cubed here. I've got x times 3x squared. I've got sums of x cubes. Maybe they can cancel. for the right power, maybe it can cancel. And that's the observation here, is that we can guess basically y equals x to the r, and that will maybe get us something, right? So let's try it out at n equals 1. N equals 1. So this would be guess y equals x to the r. What do we got? X times r x to the r minus 1, right? Plus a1 x to the r equals to 0. And so this gives us what? This gives us r plus what? Plus a1 times x to the what? X to the r equals to 0. I guess I should have told you, we need to keep things simple, we're going to assume that x is greater than 0. Now, of course, you could let x be less than 0, but then I'd need to stick in some absolute value of x's in different places, and I'm going to be lazy and not do that. So if x is greater than 0, what does this force us to choose r to be? See, a1 is given. Yeah, so therefore, r equals minus a1. And so, for example, if I was to solve x, y prime plus 3y equals to 0, I could just use what? Y equals what? X to the minus 3, right? Hey, that's new. We didn't have those before. That's not something we've seen as a fundamental solution previously. But, you know, that also doesn't, what's the domain of that? It gets into trouble at 0. Yeah, x can't be 0, exactly. So it's picking up on that domain of the definition of the differential equation. It's not, you know, there's something going on there. So that's the characteristic equation for the first order problem, right? Essentially. How about the second order problem? Bailey, do you have all this? Second order problem. We have x squared. What happens when you differentiate? Again, we're going to guess y equals x to the r. We'll grow past this and take an operator perspective very soon, but I just want to show you this way of thinking for a minute. So this is r minus 1 when I differentiate twice, x to the r minus 2, right? Plus a1 r x to the r minus 1 plus a0 x to the r equal to 0. Again, you can factor out and x to the r equal to 0. And so this implies that r times r minus 1 plus a1 times r plus a0 is equal to 0. That's the characteristic equation for n equals 2. Now, it's quadratic. It might have real solutions. It might have a repeated root. It might have what? I mean, it could have a complex solution even. And the story we told in the constant coefficient case repeats here. So if it's repeated, how can we find the second linearly independent solution? With the awful boxed formula. We don't just multiply by x. In fact, multiplying by x won't do it. It turns out when you apply the box formula, it makes you multiply by natural log of x. So for example, let me just give you some examples. I don't know, now I have a hard time making up examples, right? Like the constant coefficient case, it's easy for me because the characteristic equation, it directly mimics the differential equation. Now here, it's somewhat removed, right? So, I mean, we can try some different cases. Let's see here. How about like x squared y prime prime plus xy prime equal to 0. What would that give us? R times r minus 1 plus r, right, equals to 0. What would that? So actually, that would give me what? R squared equal to 0. Okay, so that is the repeated root case I was looking for. So that means that y1 is equal to x to the 0, which is just 1. To find the second linearly independent solution, we do what? It's y1 times the integral of 1 over y1 squared, the exponential of minus the integral of, what was it? Say again? B over a. So x over x squared dx dx. This is nice enough. That's 1. This is what? Exactly. So this is the integral of the exponential of the natural log of 1 over x, because x is positive. Bailey, you getting this? And so, hey, oh, I think I've done something. Oh, I'm an idiot. No. Oh, no. Did I remember the box formula wrong? Yeah. No, you're right. y1, 1 over y squared exponential minus b over a. All right, okay. So then what? Yeah, so this is 1 over, so it's minus the natural log. Right, it would be this, right? And then, like you said, that gives us, it gives us integral of dx over x, right? Because we still have another integral to do. And that is what? Natural log of x. It's just like I was telling you without proof. So hence, y2 is equal to y1 ln of x, which is just ln of x. That's not special to x equals, that's not special to r equals 0. That happens whatever r is. When r is a repeated root, you get natural log of x times the first thing. That gives you the solution set. If r is complex, then you get a single complex solution, and then you just have to understand what does it mean if I have x to the alpha plus I beta. If that happens, if you get r is equal to alpha plus I beta, when you solve this, what do? You do x to the alpha cosine beta x plus I x to the alpha sine beta x, and these guys are your y1 and y2 by the complexification procedure again. If that's what it worked out to be. Now, obviously, this you don't want to try to. I personally don't want to try to carry this further to higher order, right? I want to come up with a better way of thinking about it with operators. So let me talk about that a little bit. The operator argument here is a little subtle. Constant coefficients are very forgiving because the derivative operator and the constant multiplication, those just commute, and so do sums and products of them, right? So the algebra of a polynomial in the differentiation operator is very forgiving. This, at the moment, is not, and the reason for that is, can I erase this stuff? So you guys have seen already, if we have xd, well, basically, if I have xd minus lambda, right? Xd minus lambda times y equal to 0. We know we have y equals x to the lambda, right? And let's see here. So if we have xd minus lambda squared, what's that give us? We still have x to lambda, right? And what else do we have? y2, yeah, natural log of x to lambda. Assuming, of course, lambda is real. Otherwise, well, okay, I mean, yeah. I'm assuming lambda is real right now, obviously. And then what happens when we get to the third power? Huh. I don't know all of a sudden. Let's investigate. xd minus lambda to the third power. You guys, you make an ansatz. What do you think? What should we add for the third order term? I already know those first two are going to work, basically, because when you feed those into the square, I know you get 0. So if you hit x minus lambda, xd minus lambda on 0, you still get 0. This is a linear transformation. Yeah, that's what I mean. Let's try that out. So natural log of x quantity squared. Let's try that out. On x to lambda, does that work? Let's see here. So that's x minus lambda, excuse me, xd minus lambda is quantity squared. And then we've got, what, x times the derivative with respect to x of natural log of x quantity squared times x to the lambda minus lambda natural log of x quantity squared x to the lambda, right? Differentiate, what happens? I get what? I get lambda x to the lambda, because this x times the x to the lambda minus 1 from the differentiation leaves me that. I'm just differentiating this term first to get that when I multiply by that, right? And then plus x, what happens here? Times 2 ln of x, right? Times 1 over x, right? Times x to the lambda. That's it, right? From the chain rule, natural log x times 2, 1 over x, because that's the inside function. I still got the x from out here. I subtract lambda times natural log of x quantity squared, x to the lambda. Thankfully, that cancels with this, like we wanted, right? Sorry about the green. Will you survive? Is it too horrible? Okay, so that would be 2 ln of x times x to the lambda, but we already know that that is killed by this. So it looks like you're in business. So I believe we can prove inductively. You can prove by induction. You can prove by induction that xd minus lambda